I apologize to some of you who heard this, who have this going to have this feeling of deja vu because you heard this talk 2 weeks before. But I hope even you would find something a bit different, at least in the latter half of the talk. Okay, so the talk was, this work is actually not yet written up, but it's in progress, and it's being done with these two young people, both of them postdocs. The laser pointer is here. No, it's here. Yeah. So Deepak is just now a postdoc Humboldt Fellow in Berlin. Christian is a postdoc, also Humboldt Fellow in Düsseldorf. And Deepak, many of you maybe know because he finished his PhD with Sanjeev now, I think almost to the day, 6 years back, something like that. But part of this work it's built on earlier work also done with Francesco, who also maybe some of you know was Satya and Gregory Scher's PhD student, and now a postdoc in Oxford, I guess. Yes. Okay, so the motivation for this work is this phenomena of resetting, which you're going to be hearing more about in other talks in this meeting. But just so we are on the same page, I just wanted to say what it's about. And this is this, okay, so this very, very, very incredibly simple model, which however shows a lot of interesting behavior, introduced by Satya and Martin Evans 2011, and then there is this recent review. And the idea is the following, that you have something, a Brownian motion in a potential or whatever, and it's doing whatever it was doing, and then you at some point reset it back to some location. Okay, and in the simplest version, you just do this at, the times between you're doing this is just exponentially distributed with some rate r. That's it. So it's an incredibly simple model. Particle is doing whatever it was doing, and then you reset it. And then it starts again doing something, and then you reset it. And then it does whatever again, and then you reset it, and it just continues like this. Now, if it was just Brownian, if it was just motion in a potential that it was doing before, that's not very interesting. You know that it's going to settle to some Boltzmann distribution. However, this resetting makes this a non-equilibrium steady state with a non-equilibrium current. It's given by the simple Langevin equation, which is just called, it's an overdamped Langevin equation here. So this is just its regular motion, and then this is its resetting process here. Okay, so the interest, of course, is that it gives you a non-equilibrium steady state. And then this non-equilibrium steady state, actually, you can often analytically get, because it's, there is a very simple sort of renewal structure. Once you've done this, it's forgotten whatever it was doing before. So you can kind of build in this renewal structure to often analytically get this non-equilibrium steady state. So there is an interest from the theoretical aspect, but there's also an interest just because it's a process that appears, naturally, it seems, in many cases in biological processes. It's a process which facilitates search. So imagine here, and this was done in the first paper, that imagine that you are looking at first passage for a particle to reach, say, somewhere here. If it was just Brownian motion, the average first passage time would be infinity. But just because you're resetting it, you're somehow localizing it. The first passage time, average first passage time, is something finite. So it's actually, and then you can actually, as a function of r, optimize this time even. So there is some value of r for which it's really the best possible, first passage time for that particle to reach some place. So those kind of properties made this an incredibly interesting phenomena, and there's a lot of work on this. Okay, so now, of course, we were at this point interested in, okay, so it's very nice, but what would it cost you to do that? Okay, so suppose you were actually going to do this thing in the lab. What would it cost to do that? And what do I mean by cost? I mean that you could imagine that I'm implementing it somehow. Maybe I'm putting a particle in a laser trap, and I'm doing something to the laser trap. How much work would you have to put in to do this resetting? So that's a cost. So here is something, the particle is doing something, and then I reset it back to some position. How much work would it cost you? So here there's also, so the notion in which I'm going to talk of resetting is not actually resetting it to a position. You could also imagine resetting in this sort of another sort of avatar of resetting, where you could say that the particle was in some steady state, and then you want to you put it back into some state, say a Boltzmann distribution. So every time, instead of saying you reset to a position, you say, okay, I do something such that it gets back to a Boltzmann distribution. All information that whatever it was doing before is lost. And then I restart the process again. So, okay, so you can think of resetting that way too. And in either way that you think of it, you can think of a cost of work, or you can think of a cost of heat dissipated. So let's say that you don't know the mechanism that actually did that resetting, but maybe you have trajectory data, and using, the stochastic thermodynamics formalism, you could actually find out the heat dissipated, etc. But if we think of resetting in this way, let me see, what was I going to talk about? Yeah. So you could also think of, interesting things like bounds. Okay, what is the bound that you would have to, so what's the minimum cost, minimum heat dissipated, etc. And I should say that this is not the only two ways to define costs. Maybe you don't need to define thermodynamic costs. You can define costs in other ways too, and you'll hear about that in the next talk by John. Okay, so in this sort of, in this way of thinking of resetting, the particle is in some state, and then I put it back into some, so it has some probability distribution, and then I transform that probability distribution by some process to some other probability distribution. This phenomena is very much like the phenomena of erasure, information erasure. We know, so that if I'm transforming an equilibrium distribution to another equilibrium distribution, then we know that there are, the bound on the work is the free energy difference. Okay, so for the moment, let's just say we are in some isothermal. So I'm not talking of two different temperatures. I'm talking of some isothermal process. Here it doesn't matter, but for the following. But in any case, if I'm transforming an equilibrium distribution to another equilibrium distribution, we know from the second law of thermodynamics that the work is bounded by the free energy difference. And when the work is exactly the free energy difference, then there is no extra entropy produced in the system. So that we know from some thermodynamics, elementary thermodynamics. And there was actually, very, very nice experiment done a few years back now, where they looked at it in the context of bit erasure. So that's the Landauer principle up there in the title. So you have a particle. It's an equilibrium in a single well, and then you sort of manipulate these wells so that you become it's actually you manipulate it such that you force it into say, let's say, one state. So that's called erasure, because no matter whether it was here or here, you don't need to know the initial state at all. If you do that sort of set of manipulations, it always ends up there. So that's called erasure. And then it's bit, because in a coarse grain way you can say here it had two possible states, here it had only one state. Okay, so you decrease the entropy by log 2, and so if I did this process very, 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 very slowly, okay, such that the system always remain more or less in equilibrium, then, and here is the work versus the time that I take to do this set of manipulations, you see that this dashed line here is the log 2. Okay, so if I do this very, very, very slowly, so our sort of intuition from thermodynamics is that if I do a process very, very, very slowly, I pay the least cost. Like so because then I pay only the cost of the free energy difference. I stay in equilibrium all the time. And in fact, that's what they find here, that if they do it very, very slowly, you see that this curve this is the work, let's say. The line is some fit that they do that we're not interested in, but the points are their experiments. And here you see that when they do it very, very slowly, this is sort of asymptoting to this log 2 here. But if they don't do it slowly, then of course you pay more, right? So suppose I'm here, then what's happening here is that the system, when I stop the system, I maybe start in an equilibrium state. But when my process stops, the system is not in an equilibrium state. It's an out of equilibrium state, right? So what happens then? What happens if I go from, say, so what is the minimal bound on work? So equilibrium to equilibrium, I know it's free energy difference. Suppose I go from equilibrium to out of equilibrium, or out of equilibrium to equilibrium, or out of equilibrium to out of equilibrium. What are the costs that I pay for all such processes? Okay, so that's the kind of question that people ask in this whole erasure community. And there was this work, there were a bunch of different works, but I'm citing this one, particularly Esposito and Van den Broek in 2011. And what they say is that just as there was a equilibrium free energy difference, there is a sort of non-equilibrium free energy difference. If I typically go from a non-equilibrium state at time 0 to some other non-equilibrium state at time t, then the cost, okay, is somehow related to the difference in the Kullback-Leibler divergences of the final, so the Kullback-Leibler divergence of the final non-equilibrium state to its corresponding equilibrium state minus the Kullback-Leibler divergence of the initial non-equilibrium state to its corresponding equilibrium state. So imagine that I have a potential U, and for some reason the system was out of equilibrium. The corresponding equilibrium state is just the Boltzmann in that U. Yeah, so this particular result is when you have such a corresponding equilibrium state. Actually, I mean, that's a good question, because I'm sure there are corresponding results when there are other temperatures and other stuff, but this is very specific to one reservoir at temperature T, where you can define these corresponding. But of course you can also define, so you can also say the initial state was out of equilibrium, the final state could be equilibrium. I mean, you could do all those variations. The point being that when, so this is just a sort of generalization of our second law. They call it the generalized Landauer, non-equilibrium Landauer principle. That's what they call it in this paper. Okay. So there was actually a lot of interest, and there was more work on this also in this paper, Prosman et al. In 2020. And what so you see there are two interesting aspects with this erasure, right? I mean, one is that you could be what you're trying to do is convert one probability distribution to another, where either or both of those could be out of equilibrium. The other interesting thing is that maybe you're trying to do it in finite time. You don't want to spend an infinite amount of time doing it. You want to take a finite amount of time to do it, right? If you take a finite amount of time to do it, you pay an extra cost over this non-equilibrium free energy. And this extra cost is also very interesting. This extra cost is actually related to the total entropy dissipated. Remember that when the average work is exactly the non-equilibrium free energy, for some reason you're not dissipating any extra entropy, this extra cost actually is related to the entropy dissipated. It seems to always have this kind of form, where this B actually is given by something called the Wasserstein distance. Okay, so this was a Kullback-Leibler distance, this is a Wasserstein distance, which is actually also very interesting. And there's a lot of work now related to these kind of geometric aspects of this stuff, okay. But in any case, all these results exist for erasure, and we were interested in, okay, so if we think of it in the framework of resetting, like, okay, so how can we concretely see this? So there are a few differences and similarities which I'll mention. So if we are going to think about this in the context of resetting, we should be a bit concrete and the most generic. So as I said, the concrete case is that we have these what are called intermittent potentials. So as I said, we are coming back to thinking about our resetting, and we are going to say, okay, fine, so the particle is moving in some potential u, okay, and then so it's doing its own thing. Then I want to reset it, I just sharpen the potential. I just make it sharper. And then I wait till it equilibrates in the sharper potential. Typically maybe 3 times. I mean, numerically you see 4 times the relaxation time in the potential, something like that. So the particle is doing its own thing in some U potential. I sharpen it to a V potential, wait, it resets. Then it goes back to the U potential. How long it stays in the U potential is up to me. I mean, the most generic case is that I just choose my exponential waiting time, but I could choose something else also. Okay, so it's as simple as that. It's just intermittent potentials. Turn on confining potential, turn it off, etc. Okay, so here it's the confining potential. I turn it off, etc. So it's called intermittent potentials, and actually well studied for steady state first passage properties. And even actually for thermodynamic costs in several papers where Arnab is also included. But in the difference with those papers is that they don't consider, so there are different ways that you can think of a particle being reset. So the way that I'm considering it is that I say, okay, I turn on this confining potential and just wait till it reaches Boltzmann distribution. Experimentally, that's very, very simple. But in some of the papers that people have looked at before, they say, okay, I turn on this confining potential and wait for a first passage property till that particle reaches whichever point I wanted it to reach, say the origin. So then it would be like more directly like resetting to origin. So, which is a bit more complicated, but it can be done and also has very interesting properties. But as I said, whenever I say resetting, I just mean it reached a Boltzmann distribution. That's it. That's all I mean. Okay. So of course, when you keep doing this V, U and V and U and V, etc., the particle will reach some non-equilibrium steady state eventually. Okay. And anyway, so as I said, we were also motivated by this experiment. So there's an actual experiment done where in this paper, and there's another paper too, and Satya is involved, where they actually confine a particle to a trap, and here of course they are interested in different properties. They're interested in first passage property. You see here they're interested in when did the particle reach this, what is its steady state, how does the experimental data compare with the theoretical values, etc. But they do pretty much a very similar thing basically. So resetting, as far as they're concerned, is just equilibration in a trap. Though I think in this particular case, correct me if I'm wrong, Satya, but there isn't a U and V. There's just Brownian motion, and then there's a U-turn on. But okay, so it's just a variation on that. So we were motivated in this and thinking of resetting that way. So it's quite simple. So our particle is then given sort of okay. So maybe I should also mention here that and also here that you can so you turn off the trap, you turn on the trap, and the first sort of problem we looked at is when you can kind of do it instantaneously. I mean, that's the easiest sort of way to do it. So that's why I had written instantaneously there. Okay, eventually I'm going to look at the case where you turn on the trap not instantaneously. Okay? But the first set of problems we looked at was when you, so the work is of course, so the description is just a simple overdamped Langevin equation in a trap which could be changing in time, and then the work is defined in this particular way. Okay, and then you see, so here is this time, and here is my potential. So this is not a particle trajectory. This is just in the potential space and time. And so turning on and off is just, here is the particle in U. The particle always spends the same amount of time in V so that it has time to equilibrate, but it can spend different amounts of time in U taken from some distribution. And if they're turned on and off instantaneously, the work done in a time t or the work done in a reset is very simple. It's just change of potential energy here plus change of potential energy there plus change here plus change there plus change here plus change there, etc. That's it. So I just in a trajectory of time t, I just add up all those changes, and then that's the variable. I can take the average, I can take this second moment, whatever it is. Okay, so that's the, I think I'm going a bit slower than I should be. But I still have time, 15 minutes? Yeah, okay. Okay, so this was some work we did, yeah, maybe we don't need to go into details because, so this was where we turned on and off the trap instantaneously, and you can write a moment generating function and get the means, etc., etc. But you see, that still doesn't tell us anything about bounds. Okay, so I turned on and off the trap, I can calculate the thermodynamic cost there. It doesn't tell us anything about bounds. It doesn't give us this analogy to erasure where I can try to think of, what should I do to pay less? I mean, I would like it to cost less. So what should I do so that it costs less? Okay, so from that point of view, from that motivation, we looked at this case where it's the exact same thing. There's a potential U, there's a potential V. I just take my time to turn on this potential, that's all. Okay, so remember that if I'm, so now for all practical purposes, let's forget that I'm actually doing this. I'm doing this again and again and again, and the particle reaches a steady state. But if you're only interested in mean quantities, let's just look at one particular reset, okay? The particle was in equilibrium at V. I turned it off and I went to U, and then it remains in U for some time. Then I turn on the potential, okay? And now all these different lines are to show you that I could choose different protocols. So when I say protocol, I actually mean that I have a certain way to turn on this potential. Maybe I turn it on linearly so that it linearly goes from U to V, or maybe I use something else, okay? So for every different protocol, I pay some different cost. You could ask what's the best way to do it, right? So what's an optimal protocol? One could also ask that. So I'm going to be interested in that too. So I hope the problem is clear. Basically, we are looking at one specific reset and we are looking at the cost. Now, if I'm just looking at the average cost, it's just the jump here. So I'm assuming that I switch off instantaneously, but I switch on slowly. So the cost here is just the sum of two terms. Whatever is happening here plus this. So that's the work cost. Because these are the only two places where I'm manipulating my laser trap, right? So the cost is something here and something here. So the something here doesn't need to concern us at all because that is whatever it is, that's the same. What is going to concern us is this one, okay? So here is where I can actually turn it on fast, I can turn it on instantaneously, or I can turn it on slowly, okay? So this was also actually motivated by a talk we heard from Remy some time back, and there's a paper on the archive, also newly updated, where they actually looked at exactly this. They have a potential V, a potential U, and they turn it on using a certain, and they were interested in these kind of things, and they turned it on using a certain protocol, which I'll just show you. Okay, so as I said, the cost is just a sum of two terms, a W1, which is this, and doesn't need to concern us, and then there's a W2, and in this W2, we have to take into account lots of things. We have to take into account what was the state here of the particle. The state here of the particle is some kind of time average state that's related to the fact that it was in the equilibrium in the other potential. Suddenly it found itself in this U potential. It's evolving in the U potential, so there's a propagator there. At some time, this other thing starts getting switched on. So the state here is some time average state that takes into account how much time it got here. And then I have to take into account all the thermal noise while I'm turning on this potential. Okay, so I have to take into account all these things, but these are all harmonic potentials and we can do this, at least for averages, it's not bad. Okay, so just to be a little bit concrete, let's see the time, I have about 10 minutes, yeah. So just to be a bit concrete, the experiment that Remy et al. Did, they used some potential like this, lambda u plus lambda v minus u tanh. So they turned on the potential this way, and you can see that if I'm very large, if I'm doing it very, very slowly, it's just linearly turning it on. Okay, so suppose we just take our exponential time distributions to be in the u potential. Then there are just three parameters in the problem, three non-dimensional parameters. The TV is the relaxation in the V, Tu is the relaxation in the U, and TSW is how long I take to switch on the potential, and R is our rate here. So everything that I find must be some function of these things. So W1, as I said, we don't need to worry about. There is a W, the W2, remember, was the work that I go from here to here, which of course depends on the time that I take to do it. Now, two very simple limits are when it's instantaneous or when it's slow. Okay, when it's very, very slow, what do we expect? We expect it to be the free energy difference, and you can show that it is. Okay, when it's fast, then also you get some expression, and of course our intuition tells us that the fast should be more than this. You pay more when you turn it on fast than when you turn it on slow, but that's not the case actually. So this is just to show you that these are 4 different parameter values, and the dashed line here, so wherever all this saturation here at late times is always the free energy difference between the 2 traps. Okay, the free energy difference between the trap V and the trap U, that's it. But depending on parameters, it can be doing whatever. So here in this parameter, it seems to be behaving kind of normally, but in other parameter regimes, it's some other cost is lower. It can be non-monotonic, so it's doing whatever. Okay, so we were a bit interested in understanding if what does it mean and what are the bounds on this. You see, so what are the bounds would mean? Okay, so here, the free energy difference is lowest, but here something else seems to be the lowest, and here something else is the lowest, etc. So we were interested. Actually, so we can actually also, it's rather interesting. There is this. Yeah, so there is even a phase diagram. So if you look only in this region below the red line, because that's where the V trap is sort of steeper than the U, then you see there's a region here where the free energy, the free energy difference, it actually pays to do it faster. So in region 1, it actually pays to turn on the potential faster. In region 2, it pays to turn it on slower. But that's not the end of the story. It's even non-monotonic. There are even non-monotonic regions in 1 and 2. It's related to this particular protocol. Anyway, so we understood all that. But you see, that's still, you can't say that's general, because that's related to a specific tanh protocol, that protocol. So now you can actually ask a question about optimal protocols. Okay, so suppose I have, so this work thing, this W2 is a functional of this lambda. What is the best lambda? Okay, so, and you can actually find an answer in the case of this very simple harmonic potentials. So basically the idea is that, okay, W2 is a function of lambda, minimize this and you get an optimal protocol.
About 5 minutes.
Oh, yeah, yes. So 5 minutes to 35. Yeah, okay. So I'm almost done. So the optimal protocol, so basically we have to calculate our W2, I mean the same as we were always doing. And there is a way to calculate, just because these are all harmonic potentials, there's a way to calculate this optimal protocol, minimize W2 as a function of lambda t and get this optimal protocol. And it was actually done in another context by Schmiedel and Seifert. But they were looking at transforming an equilibrium to another equilibrium. Okay, so in our case, remember that the system is in some steady state or some time average state, and then we transform it. Okay, so what does this optimal protocol look like? It can look kind of strange. It can look like this with jumps. So there is a jump in the beginning, you jump to some place. Okay, so there are reasons for this. Maybe we don't need to discuss it right now, but I'd be happy to discuss it if you're interested later. And then, there is some change and there's a jump later. These initial jumps are always there. The final jump depends on the parameter, etc. So optimal protocols can look quite strange in this context. And the W2, as you see, there are parameter regimes where you actually pay less cost than the free energy difference. There are regions where you pay more or you pay less. Okay. And then, so this, you get this, so the optimal protocol is way better than the tanh. So for some parameter regime, you see that the tanh protocol is doing something like this, the optimal protocol is doing something like this. The interesting thing about the optimal protocol is that it's always monotonically decreasing. And what is the value that it decreases to here? That's not the equilibrium free energy difference. It's this non-equilibrium free energy difference. Okay. So this optimal protocol is always monotonic and it decreases to this non-equilibrium free energy difference. By this bound, I mean this Esposito. Okay, it's not. Yeah, so this dashed line is this Esposito-Vandenbroek result that I showed you. But our protocol actually is always, you see, so this is the difference of the red line in this region with the bound, and there is always some difference. And the reason that we understood that, the way that we understood that, and that's really thanks to a nice insight that Christian had, is that, okay, what is this optimal protocol telling you? It's telling you, okay, change your potential this way or that way, change it so that it matches my non-equilibrium steady state. But given a harmonic potential, I may not be able to do that. I mean, with the harmonic potential, I only can do so many things, right? So what we found is that we have to actually project our time average, whatever steady state, to some sort of Gaussian state that could be produced by the harmonic trap, and it's the Kullback-Leibler difference of that state with. So here, remember, in the Esposito case, it was the Kullback-Leibler of this whatever steady state you had with the equilibrium state, but we find that it's some kind of projected state to this equilibrium state. Okay, so that's just some results we have. We have expressions for all this. Whether this b is the Wasserstein distance or not, I haven't yet been able to do the calculation, but we expect that it is. We can see that this b, for example, is always positive, etc. So that basically it's so we've looked at the steady state erasure process. Okay, so we call it steady state erasure because it's like resetting. You keep you erase, the system evolves, you erase, the system evolves. So there is a steady state there, and there is this resetting cost. Okay, so as I said, we haven't yet. We hope to be able to finish this soon. So there's a lot of interesting things I think we could do. There are experiments where Yael has also been involved, things with feedback, things where you have trap centers, where Arnav was also involved, where if you don't only sharpen the trap, you can actually move the trap too. Okay, so maybe you can do both. You can move and you can sharpen. So there's a lot of like different manipulations where you can actually do this exact optimization procedure. Okay, so that could be interesting. You could do this thing for first passage problems, in the sense that all this I've only been talking about the cost, for one single reset. But you could also think of the cost for this whole, so I have a first passage problem, and you could ask, what's the total cost up to first passage? Okay, and I think, and you can also talk of different cost functions for such problems, which you'll hear about in the next talk. Okay, so with that, I'd like to say thank you.
Questions?
Sorry. So how did you find the optimal protocol for, like, you have shown a particular choice of lambda of t, like going up, and then, like, how did you find that?
So there is this procedure, we can go into more details later, where you can actually, so this W2 is a function of this lambda of t. And then, so you can write this functional, and then actually you can write everything in terms of, because it's this, harmonic trap has this x squared, you can write everything in terms of this, the variance. And then you get an Euler-Lagrange equation for this variance, and then when you put it back in the expression for W2, you get a certain, or rather when you get the variance is related to lambda. So when you solve the Euler-Lagrange equation for the variance, you can put it back and get a lambda star there. And then of course you can do this for different parameters. And then you can get, so the as I said, these optimal protocols can look like this with weird jumps. You jump in the beginning, you jump in the end, or you jump in the middle, or whatever. You can have difference, which costs less than if you were just trying to continuously do something.
So this one, does it also include the realization where it overshoots and comebacks? Like means
Overshoots,
I mean in the sense that finally you want to go from lambda 1 to lambda 2, right?
Yeah.
So this one is basically throughout it is always bounded between lambda 1
Yeah.
and lambda. But this, when you do this optimization, does it also include those trajectories which overshoots, let's say lambda 1 to some lambda 3 and
come back.
come back, or it's just only constrained with those things which just
So of course, when we do the Euler Lagrange, we put the constraints only in the beginning and the end.
end.
So we want to start with the potential, we end with the potential. In principle, you could overshoot, I suppose.
So
But we have never found any which overshoot.
Okay.
But I don't see why you could not do it. Maybe you could, I suppose.
Okay.
Yeah, that's interesting actually. So as I said, so the erasure problems often say, I want to change one probability distribution to another probability distribution in a certain amount of time.
Yes.
Here we are doing things slightly different. We are saying, I have a trap with one stiffness, and in a certain amount of time, I change it to a trap with another stiffness. Yes. So it's a slightly different kind of question.
Yes.
But I don't see why you can't have overshootings, except that we have never found one so far.
Okay. Any other questions?
Bit naive question. So, if you only have the trajectory of the particle or some process, can you? Is it possible to obtain the cost function, or what other information?
From the trajectory, from the stochastic thermodynamics, you can actually get, for example, entropy production, because it's log of the probability of a forward versus a reverse trajectory. So whenever a reverse is definable. In the sense, so in the original reset problem, a reverse is not definable, but there are variations of it where you can define, and then you can get something like an entropy production, and then you can show that actually it's consistent because it's heat dissipated, and heat dissipated must be related to work done in steady state. Right? So by first law, if the system's energy is not changing, average of one should be equal to the average of other, and you can show that it matches.
Thanks.
Excuse me. Can you explain the difference between the blue and the cycle and what you obtained in the resetting process? Blue and the cycle.
With the erasure process, you mean?
Yeah.
Well, actually, just now it looks pretty much similar.
Very similar.
Yeah, because we get a non-equilibrium free energy difference. We get something that is possibly this Wasserstein or whatever it is. But actually, we were just happy because we understood it in a very concrete manner, sort of with these potentials, which you can actually manipulate in the lab as well. So that was, but for the moment, it looks rather similar, I would say.
Okay, so let's thank Supriya.
Thank you.